Okay, should we start? Okay, so good morning. Um, this is my tutorial Pointers in Python. My name is Yan. I'd rather not to pronounce my last name because I'm not sure I will get it right, even myself. But okay, I'm a software engineer at a company called Kiva.com. How many of you heard of Kiva.com company? Okay, you should. You must have been from Europe. Okay, yeah. We are an OTA, a very popular OTA in Europe. OTA stands for Online Travel Agency. We basically sell flight tickets, to put it in short version. I work in a search engine team. So every time you search, you look up for a flight, it goes through our team. You may in this tutorial, you may see me struggle a little bit because this is my first visit to US and jet lag is taking its toll. I'm still not really recovered. So there can be some roughness. So if I screw something up, don't be mad at me. But I'm pretty good at improvising, so we'll figure something out. And before we start, how many locals are here? I'd like to know how many guys from Pittsburgh are here. All of you are from Pittsburgh? I have to talk to some of you after this presentation, so please. Anyone who wants to talk after this session, please approach me. I'll be here today, tomorrow, and until Monday, I guess. First question is, how many of you have Mac OS? How many of you that have Mac OS have Docker installed? Okay, for those of you who don't have Docker, I cannot guarantee that every single thing that I'll be showing will be working for you, but you should not be sad because this workshop will be step by step reproducible. There will be a GitHub link that I will share later. It's not done yet, but I will do it. We'll need to sync in something like Discord or something. Not sure yet. But there will be a 100% reproducible version of this tutorial. So if something doesn't work for you here now, just sit and watch. It's not the end of the world. You'll still be able to reproduce it later. Okay, for those of you who have Linux, how many of you have Linux? Okay, for those of you who have Linux, you should be fine. And for those of you who have Windows, I cannot guarantee unless you have Docker. How many of you have Windows? Okay, that's sad. But okay, as I said, I cannot guarantee, but if something doesn't work, as I said, don't be sad. There will be a handwritten like tutorial step by step, the same as we'll have today. So I have to thank my company for supporting me in this. If you want to know more about us, scan the code. No one's scanning, okay. So who am I? As I said, I am software engineer at Kiva.com. Also, in my spare time, I am a CPython sponsor, and sometimes I contribute to CPython. Before we start, I want to say that you can stop me anytime you want. Just interrupt me if you want to ask some question. If it doesn't work, don't worry. As I said, it will be a tutorial on GitHub, reproducible. If you don't understand every single detail, also don't be sad. You're not supposed to. If you understand, it's great. If you don't, you can pick up those things that you don't understand later and revisit this tutorial. There'll be a lot of hard stuff here today. And how many of you have C experience? Okay, most of you. How many of you that have C experience have experience with pointers? Okay. If you don't know what the pointer is, don't worry. I'll be explaining shortly. So there is no requirement for C as well. So before we start, we need to make a setup. This is when we find out if it doesn't work for you specifically. So I want you to go to this link. I hope there will be not a lot of typing. And there will be a README with instructions of what you have to do. If you don't have Docker, don't do the steps that start with the Docker title. Just skip them. And we'll see how many of you can get it going. It should take you about 5 minutes or so. Hello. So once you're done, just raise your hand that you're done. Okay. How slow it is? How many percent does it say? 0. Yeah. At least it says something. So you're cloning a repo, right? Okay. Let's see if I can somehow improve it. So how many percent? 32. Okay. Okay. That's a possible fix. I already notified staff. If nothing can be done, then I guess the worst case is I just show through presentation, and you'll be able anyway to reproduce it at home, which sucks, but at least something. I apologize. I have Mac. I have Mac, but I don't have a USB adapter. Hmm? So let's wait a couple minutes. They're working on it. I did a dry run, and it took me about 2.5 hours. So we have a half hour of some time, you know. Hmm? 3.9. Mm-hmm. You're cloning two separate repos. Mm-hmm. Just do as it says. There will be a step removing the repo. So you clone the CPython repo, you cd into it, and then you do everything else. Hmm? Yeah. So how many of you have already cloned the CPython? Okay, that's nice. Not too bad. People have phones. I apologize. Something I didn't anticipate. It's getting faster. As I said, we notified stuff. So how many of you don't have the repo clone yet? Okay. How many of you have completed the steps with no error? Okay. What is it? So once you complete all the steps, you should be getting something like I have on the screen. What is it? Okay. I think it's too late for that. So how many of you have already all steps completed? Okay. What do you have? You have Windows? So for those of you who use Docker, you do everything inside Docker. So once you log into container, you continue doing everything inside container. Because I see some of you compile and then switch to the other tab of terminal and try to execute. And obviously you're not inside Docker, you have a different OS and it fails to execute. You should get a python.exe even if you are on Mac OS. So it's either you get Python without exe or python.exe, but exe doesn't mean that it's only for Windows. I assume everyone has have already cloned the repo, right? 15? Oof. You shouldn't have said that. How many of you still downloading? Okay, there are a few. Yep. If you don't have Docker and you have an error, you're the unlucky one I was mentioning that will be just sitting and watching. But again, as I said, it will be 100% reproducible. Once you set your environment at home, you can follow the steps and you'll get the same result as we're going to get today. Okay, so once you finish all the steps, you are going to get either python.exe as executable or just Python without exe. For those of you who are on Linux, you're going to get Python without exe. How many of you have an executable already? Okay. How many of you are still downloading? Oh, I don't think we have time to wait, so I apologize. Don't be mad at me. How many of you still compiling? Okay. How many of you are able to follow me right now? Okay, let's wait 5 more minutes. This is the longest step, and this is the only step that we'll have to do. Also, once you clone the repo, we'll be doing everything in terminal, inside Docker. If you have Docker, if you don't have and it's working, do it inside without Docker inside terminal, but open the code base inside your favorite IDE or code editor. I'll be using VS Code. Can we get lights off in the middle? Is it better? Even better now. Should be perfect. Okay, it's been 5 minutes. How many people have everything set up? Okay, for those of you who still waiting to download or to compile, I apologize, but we have to keep going. Try to catch up. If you don't be sad. Okay, so what we just did, we cloned the CPython repository. We switched to CPython 3.9, and we compiled Python programming language from scratch, so give yourself an applause. If this is your first time compiling a programming language from source. So back to the presentation. Now that I've said CPython, what do I mean CPython? To understand what a CPython is, I'd like to start with what CPython is not. First of all, CPython is not Python. How many of you thought that this is the same thing? Yeah? Okay. So CPython is what's known as reference Python implementation. It is the main implementation of Python programming language. You see, at this point, the Python as a programming language is more like a standard, like an ECMAScript, if you heard. And the ECMAScript is a standard, the JavaScript is an implementation of the standard. So the Python is a programming language standard, so to speak, and the CPython is the main implementation of it. So we cloned this repo. This is the source code for the whole main implementation of CPython, which was started back in 1990s by Guido and Rossum, if you heard about him. So this is it. So as I said, it is a reference implementation. It does mean that there are other implementations as well. So there are things like Codon, which is a fully compiled to the native machine code, Python. It's not interpreted. There is Jython, which is Python in Java, and there is a PyPy, which is the same Python as CPython, but it has a JIT compiler, if you heard about it. And here comes the very tricky question. Is Python compiled or interpreted? What do you think? Both? Who thinks it's interpreted? Okay. Who thinks it's compiled? No one thinks it's compiled. Who thinks it's both? Okay. So you see, if we take this paradigm of compiled and interpreted languages, we can see languages like JavaScript, Ruby, Lua, Python in the interpreted bucket, and languages like C, C++, Rust in compiled bucket. But if you take, for instance, a Python and compare it against Java, which is considered to be a compiled language, both of them have compiler. So for those of you who don't know, Python does have a compiler. And both of them compile to a bytecode, which is known as an intermediate representation. Both of them execute in a virtual machine. You might have heard Java virtual machine. There is such a thing as Python virtual machine, but it's not known as much as Java. And yet one of them is considered interpreted and one of them considered as compiled. And if you screw this up, you're going to fail your interview. So instead of all this compiled versus interpreted, I like to think of languages types as native and virtual. And what I mean by native and virtual is, if you take, for instance, a programming language like C, you have to pass it through some sort of compiler infrastructure, which generates a machine code, which is the code that your CPU physically executes on your machine. This is an example of C that goes through some sort of GCC or Clang, and it spits out the machine code, which can be executed on your CPU. And what virtual is basically the same thing, but except instead of the physical, the real machine code that your CPU understands, it spits out some sort of abstract code. And of course, that abstract code cannot be executed on your CPU because it doesn't understand the bytes. So there must be something between the CPU and the abstract code, which is a virtual machine layer. So as you already heard, Java virtual machine, Python virtual machine, this is the layer between your CPU and your virtual machine code. So this is the key distinction between two types of languages that I don't force anyone to think about it like this, but this is how I think about languages. And since I mentioned that Python programming language does compile, I think it should be clarified what does it mean exactly. So there is a compilation pipeline inside Python. It consists of several steps. These are the key ones. There are a couple minor ones in between of those, but they're not worth mentioning today. Those that you see, we're gonna touch some of them, not all of them. There is tokenizer, we're gonna touch that. There is a parser, we're gonna touch that. AST optimizer, again, we're gonna touch that. Compiler. The compiler in this context is the piece of code that transforms your abstract trees to the actual bytecode. If you heard the notion Python bytecode, this is the piece of code that physically, there is a compiler like the whole pipeline, and then compiler like a separate piece of code that spits out the machine, the bytecode. This is called code generator in parentheses. There is a control flow graph. You don't need to do anything with that, just for general information that such thing exists. And then there's assembler, which we're not gonna touch either. So a little bit more details about each step of the compilation. This is, if you had a class on programming languages, this will be, how many of you had class on programming languages? Okay, so some of these things that I've just mentioned should be familiar to you, right? Okay, so for those of you who didn't have class on programming languages, we're gonna briefly walk over these steps. So the first step is tokenization, which aka lexical analysis. What it does is you have a source code of your programming language and it makes it into chunks that can form sort of an abstract representation of your program. You can see this piece of code, this Fibonacci function Python, will be broken into these tokens, individual. Spaces are ignored, comments are ignored, only the vital information about program is captured. Then you have parsing. The parsing takes in all the tokens that you broke your code into, and it builds what's known as AST, an abstract syntax tree. And this is the basically one-to-one representation of your source code, but in the form of a tree. So as you can see, we have this Fibonacci function, and it turned into a Fibonacci node, which has children as the name. I hope these labels, you can see those labels on the arrows. You have the name, you have the args, and args itself will also point to a node, which points to arguments, and so on and so forth. So why do we use the ASTs? First of all, I'd like to explain what is the difference between statements and expressions. All the programming languages are composed of two main things, statements and expressions. So who knows the difference between those two? No one does. Expressions don't have value, they result to a value. So if I give you a mathematical expression, that will be an example of the actual expression. So everything that can be reduced to a value is considered an expression. And the statement is like an if, a while, a function definition. Everything that makes up a line is a statement, and everything that resolves to some sort of value inside that line is an expression. This is the key difference between those two. We will be implementing new types of expressions inside Python. Why do these ASTs exist? Why do we convert between tokens? Why do we convert tokens into an abstract syntax tree? First of all, there are a couple of reasons. Two main reasons is hierarchy and precedence, where the hierarchy is, well, I know that there is a node and its children, like the function definition. I know that its children is function body and function arguments. I know that all these things belong to a function, and the function itself, for instance, can be a child of a class node, and I know that this function belongs to the class. So there you have a hierarchy structure. And then you have a precedence. A precedence is a very important thing when it comes to evaluating expressions. If you take, for instance, this very typical 2 plus 2 times 2, you can convert it to a tree. This is one of my favorite exercises. How many of you done this type of exercise when you have an expression tree and you have to evaluate it? Okay, so you must be familiar with that. So when it comes to precedence, the lower the nodes, the more precedence the operation has. In this case, 2 times 2 will be lower than plus, and therefore this is how you ensure that the expression is formed correctly. Because if you traverse the tree and evaluate it in the right order, you will get the right result. Okay, and if you compose the tree in a different way, so instead of plus being at as the root node, and it now becomes a asterisk, which is multiply, you will get a completely different result, right? Because first of all, you do a typical depth first search, and you end up with a wrong result. So this is the precedence. So we went over the tokenizer, parser. Parser spits out AST. The next step in the compilation pipeline is what's known as AST optimizer. An AST optimizer, there are a lot of things that you can optimize your tree, a lot of ways how you can optimize it. But inside Python specifically, Python only implements one thing, which is called constant folding. So to give an example is, if you have an expression like constant and can be evaluated during the compile time, it will do it during the compile time. It will not execute the same thing over and over again. So in this case, if you have a constant expression, it will evaluate it to the constant and use it as the constant always. So this is more a real example. There is a this module. How many of you heard of the this module inside Python? So a this module is, you can pass into it a function, a string with Python expression or statement, and it will spit out the bytecode. How many of you heard of the bytecode? You should have heard, right? Okay. In this example, as you can see, it just loads the constant 6. So it doesn't, there is no 2. So it, before even spitting out the, before even the executing, you will not evaluate 2 plus 2 times 2 every time. You'll get the 6 every time. And if I change it a little bit, so instead of constants, I have variables. Now you can see that the whole sequence of instructions is generated, right? Because you cannot know in advance what the values will be. Therefore, you cannot do this optimization step. This will be very important because we'll be touching this step. And then after you formed a AST, you've optimized it. Now it goes to a compiler, the actual thing that walks the tree and generates the code. So in this example, this is just a copy paste from the previous example. So this tree will be evaluated to these 1, 2, 3, 4, 5, 6 instructions: load name A, B, C, binary multiply, binary add, and return the value. Okay, a little bit on the bytecode. Again, how many of you heard what the bytecode is? Okay, so as you've seen, there is a compiler that converts AST to bytecode. Bytecode is a low-level intermediate representation of your code. Yes, please. So if it's the depth first search was mentioned in the previous example, and therefore you think that it's the same here. This is a little bit different. Generating code is not the same as evaluating an expression. So this is the code that we'll get into that. Okay. Someone else raised hand I could see. No. Okay. So on the bytecode, once the compiler turns your AST into bytecode, every bytecode is formed of 2 bytes. The first byte is what's known as an opcode, stands for an operation code. It tells the virtual machine, once it hits this bytecode, it tells it what to do. And there is an op arc, which is the second byte. It tells for this instruction on what to do this operation. So in case of a load, for instance, you load a variable, the op arc will be an index into an array of variables inside a frame. And if you have, for instance, binary add, which is a real bytecode, it has no op arc because it operates on already loaded values onto the stack. So this is just an example. So instead of the bytecode, it should be named as a word code because the byte is 8 bits and the word is 16 bits. If, by the way, who knows why the word is 16 bits? No one knows? It comes back from the Intel on the old days when the 16-bit CPU was released. It was considered 16 bits was considered a word. This is why this should be a word code instead. Okay, so this is a really rough, brief introduction of what we will be going through. Our goal is to do something like this. For those of you who worked in C, do you recognize this syntax? Okay, For those of you who haven't worked in C, what we're trying to do is we're trying to implement pointers. What a pointer is in an unsafe language, which C is. A pointer allows you to take an address of something, and physically you can manipulate inside your RAM physically manipulate the bytes that are there. Okay, so we are trying to make Python a little bit more unsafe. So there are two operations, which is the address of, if you see the ampersand, the lower one, and there is a dereference, which is take the address of something, and this is the address of, and then get back what I took address of. This is the reference. So now we finally get to touch the code base. How many of you have compiled successfully? Cool. So for those of you who don't, again, I apologize. So, oops. If you open the CPython code base in your favorite editor, and we will go through a little, do a little code base tour. So here you have these you can ignore these. There is a doc directory, which stands for document. This is the content of it. You can see on docs.python.org. This entire website is basically what's inside this doc directory. Then you have the grammar. We'll get to that. This is the grammar of Python programming language. How many of you heard of the grammar files? Okay, cool. We'll get to that later. Then you have include. It has, again, if you worked in C, it has a lot of header files with definite declarations. Then you have lib. This is where, I don't really remember, this is this Python standard library, but it's the Python part. And this is some maintenance stuff. There's Mac directory. This is Mac specific. Miscellaneous, again, not interesting. Modules. Modules is, again, a standard library, but this is the C part. You have Python part and you have C part. Then you have objects, and objects is a directory where you could have already heard that everything in Python is object, right? How many of you heard such saying? Okay, this is the directory where every single built-in object is implemented. So we have set, dictionary, list, etc., etc. Every single object has its separate file with an implementation. Then you have parser. Parser has its dedicated directory. Again, a piece of code that takes tokens and transforms them into a tree. Then you have patches. This is what we cloned, but we're gonna need that. It's not part of Python. Then you have PC. This is Windows, never touch it. PC building and Windows. Programs is, I believe, it's something different. We don't need that. And then you have Python. Python is everything virtual machine related. We're gonna get into that. Then you have tools. This is not really interesting to us. And this is a makefile project. How many of you know what a makefile is? For those of you who don't know, makefile is a build system. Since the project is in C, Python is written in C, the build system is chosen to be makefile. Okay, did I miss something? I guess I didn't. So a little quick tour. Now we're gonna get dirty a little bit. We're gonna implement a new token. I know that the reference is an asterisk, but because of the complexity of Python grammar, you know there is args, star, quarks. We cannot implement the reference the same as in C with an asterisk, so I had to choose some different token. You can do that, but there will be a separate session of that because you'll have to re-implement the whole parser from scratch. So a little bit of a lie from the beginning. But okay. Okay, so now for those of you who have everything set up, what you want to do is apply a patch. So we're not going to be live coding. It will be too much. We are going to apply patches instead. So go ahead and do git apply patches one.patch. Is it better? No? Can you turn off the light? Is it hard to see because of the font or because of the light? Both? Uh-huh. Better? Is it better? Okay. Can I make it smaller? Still good? You don't see? Can we proceed? Okay. So what we have just done, how many, did everyone apply the first patch? Okay. So the files that we changed are, I have a little cheat sheet here. We have changed, the tokens file. Okay. Inside the grammar directory, there is a tokens file. As you can see, we have added a new token type, which is $. And the second thing that we changed is a grammar file. So there is a python.gram in the same directory. And we added this line, which says a $, a equals factor, blah, blah, blah. So in order to explain a grammar itself and a parser is a so deep and so broad topic that it will require a separate session on that. So I won't be going into deep details of how grammar works, but you should know that there is such thing as a grammar file, which describes a grammar of programming language in some sort of way. How many of you heard of BNF, eBNF? Okay, how many of you heard of ASDL and okay. So these are all the things how you configure grammar. What we have just done is we said that I want a new expression which starts with $, and whatever expression comes after the $, what I wanted to do is I want to pass it to a pyunary op. This is a function inside a, I don't remember which file it is. It's Python ast.c line 2628. Yeah, this is the function that's responsible for handling, like if the parser matches based on this rule, it'll pass it to this function and it will handle it. So what we are trying to say is whenever you hit $, with some sort of expression after $, I want to behave it exactly the same as an inversion. So how many of you know this tilde, what it does? No one knows what the tilde does? Okay, that's an inversion. So if you, yeah, it's a, let me show. So if you type tilde, for instance, some expression, it works for integers. I forgot how to switch bits in the number. Bytecode version, the complement. Yeah, this is one's complement. Yeah, so we want a dollar which does not exist yet, right? If I type in dollar something, there's invalid syntax. Okay, we want the exact same thing. When I type in dollar, I want to see $1 to spit out -2. Okay, so let's do this. What we have done, we have added some things into configurations. We have added new token. We have added new rule. But what we have to do now is we have to implement it in code. So what's cool about Python is when you have these pieces of code, which is parser, which is tokenizer, you don't have to implement the code yourself. All you have to do is you have to provide a configuration, and then there is a make. In the make file, there is a target that will generate the code for you. So there are pieces of there's pieces of software that specifically take this configuration and spit out the actual C code for you. This is some sort of meta programming to make your life easier, so you don't have to adjust the code yourself. So what we need to do, we need to update the tokenizer. So type in make regen token. This is very typical. You change something in some configuration, and then you do make regen something, and it will just generate the code for you. It's not everything, but for parts like these, there exists such thing. So you should see something similar. What we have just done is we added a token into the actual code. As you can see, there is a comment, auto-generated by tool script generate token.py. This is what gets triggered when you do the make regen token, for instance. And as you can see, for some reason it does reordering, but these were already defined, and this one was added just now. Another file that was changed is token.py. Yeah, as you can see, it was added $1. Again, auto-generated by tools, generate token.py. I need to explain why some of the things are in C header files, C files, C/C header files. Some of them are in Python. The reason for that is some parts of the build process are handled by the Python programming language itself. To make things easier, the typical way it works, you have a older version of Python and you want to compile a new version of Python. Some of the build process, some of the steps of the build process are handled by the older version just to make things simpler. This is why you see some py files and C files, okay, in the build process. And also one of the files that was changed was token.c. As you can see, there is a new line, $ inside this PyParser token names, all right? Okay, any questions so far? No questions. Okay, so now that we have modified our source code, what do we have to do? We have to recompile. So that -j means that use all the cores, just parallelize do the work faster. Compiling takes time, especially for such large projects. How many of you have it compiled? Okay, once you compile, go ahead and do $1. and it's invalid syntax for some reason. It's python.exe. Yeah, it's in the current directory. Okay, I missed one more step because we have added the token. We need to update parser as well. So make regen parser, or pgen. Pgen stands for parser generator. So you have a grammar file, and then you have a program that generates the parser code for the Python programming language based on the grammar. What is it? Make regen pgen, P-E-G-E-N. Okay, and now we compile. What we have changed is in the parse.c file, we have, as you see, there is a comment. There was added new form of expression, which is dollar based by followed by some factor, where the factor is an expression. And there will be a piece of code here, as you can see, a new piece of code that handles this specific scenario. Okay, now that you have compiled, go ahead and do $1, and you get -2. How many of you got this? Okay, cool. So what we just did is we modified Python programming language. If this is your first time, give yourself an applause. You deserved it. You modified a Python programming language. So let's wait for until the rest of you get it. Did you do regen pgen? P-E-G-E-N. After you do all the regen stuff, you have to recompile again. Okay, should we proceed? Okay, cool. So now that we have added this, just for illustration purposes, that we can do such things. Now what we want to do is we want to add new, we want to add one more piece of syntax, which is ampersand something. If you go ahead and do ampersand something, it says invalid syntax. We want to add this as well. And what we want to do is we want ampersand something to return us an built-in object that we will be implementing. And we want dollar something is dereference that. So ampersand something gives us a pointer to a Python object, and dollar on that pointer dereferences. So returns the thing it points to. So now go ahead and apply the second patch. So what we added is in this python.asdl, git apply patches slash 2.patch. Okay. What we changed is inside python.asdl file, there is a new unary op. As you can see, there is a uaddr, which stands for unary address of, and uderef, which stands for unary dereference. This will be new types of nodes in a syntax tree. The next thing that we changed is the grammar again. As you can see, we no longer do the inversion. We do the same that we just added. We do unary address and unary dereference, which we'll be implementing. And this is it. So what we need to do now is we have to regenerate the AST file. So we have new type of the node, but it's not implemented yet in the code. So again, the same practice. Make, this time it will be regen AST. Okay. After you did regen AST, what changed is this file python-ast.h. Inside this file, you have new unary op type, which is uaddress of and uderef, as you can see. And additionally, we changed the python ast.c file. There it is. So switching on the type of the node. Okay. So we have added new node types. Now that we have added new node types, it goes through parser. So we have to regenerate parser again. So make regen pigeon. And after we regenerate parser, again, compile everything. Make -j. Okay, after you compile again, the python.exe, and let's try $1, and you should get a segmentation fault. How many of you know what a segmentation fault is? Okay, so a segmentation fault means that something very terrible happened. Without going too much into the details of how segmentation faults are generated in the OS, it means that we touched some part of memory which is not ours, and therefore the OS killed the program. However, if we try to do a little bit differently, let's define a variable. Let's do a = 1, and let's do $a. And we no longer get a segmentation fault. Instead, we have a very meaningful error, which is Python error. Unary op 6 should not be possible. So the difference is only we do this on the variable and on the constant. And in one case we get a segmentation fault, in the other one we don't. What do you think it is? Any ideas? Why? Constant is not stored. Not exactly. Yeah, please. I have changed something in the memory.
No, I mean the constants are stored somewhere.
The constants are stored somewhere. The constants are stored somewhere, but it has no relation. Yep. That's right. Constant expressions, if you recall, are are going through an AST optimizer, and the constant expressions are trying to be converted into a constant, so you don't reevaluate it every time. Okay. So what happens in the first scenario? It tries to execute some code, which it doesn't try to execute in the second. And this is where we get a segmentation fault. If we go to ast_op.c, this is the file that implements the constant folding. This is a very typical technique in a compiler design. As you can see, there's a array which is called unary ops, which is called ops. It has invert, not unary add, unary sub. So this function is responsible for folding a unary operator. What it does not have our two new unary operators, right? Unary dereference and unary address of. And therefore, it indexes into something and tries to execute, and of course, it doesn't exist, so it's a segmentation fault. So what we want to do is we want to apply a plug temporarily, so it doesn't throw any errors. So what we're going to do is we're going to apply the third patch. So git apply .patch. As you can see, there is a new function called plug. It just returns null for now. This is how you tell, I don't know how to fold it, just skip it. Okay, and if we recompile, and try to execute it again, now it gives us the same error as with non-constant. Does everyone get this? Okay, questions so far? Anyone need any help? Everyone's caught up? Okay. So we are getting this unary op6 should not be possible. If we recall, in C everything is, well, to put things, to make things simple, everything is number. Let's put it this way. The unary op that we added is associated with a number, as you can see. Unary address op and unary dereference has its own number. As you can see, there's unary op6 should not be possible. If we do ampersand, we should get the 5, right? Yeah. So there is some piece of code that switches on the types of the unary operation, and if some doesn't exist, it throws an error. At least it doesn't crash, so we know we are moving in the right direction. The thing is, however, we are successfully parsing this new expression. There is an AST module. How many of you know of an AST module inside Python? Okay. So if you import AST, what you can do is you can tell him to parse ast.parse, and let's do &1. This will give you an AST node, which is module, and the module has body, and the body is the children of the module, which now we have only one children, which is an expression, &1. So the 0, I think it's value. AST.parse and in quotes as a string &1. Okay, so there's an expression. It is, if you go and do a value on it, dot value, you should see unary operator. I think it's up. Yeah, the up, as you can see, it successfully parses our expression. So you have an AST dot uattr object. But something down the pipeline is still missing. So if we go ahead and apply the fourth patch, git apply patches for.patch. What we have changed is upcode.py file. We have added new upcodes. If you recall from the bytecode, there is an upcode and uparg. We have added new upcodes, which is unary address and unary dereference. Again, this is the file that will generate them for you. You don't need to do this in C. And what we want to do is we want to regenerate all the opcodes. So make regen opcode. What we have added is opcode.h header file. And inside this header file, there are two new lines which associate our new opcodes with numbers, unary address and unary dereference, which will be 80 and 81. Okay, so we are slowly preparing to, if you recall from AST, there is a compiler that compiled into the bytecode. Now that we have successfully parsed our source code into the AST, we are missing the part in the compiler that takes the node and converts it into a bytecode. This is what we'll be adding. Now, go ahead and apply the fifth patch. What we have changed is inside compile.c file, there is a function called unary op. It accepts the node type, and it tries to spit out the opcode for that node type. So we were missing these two. Now we have those two. As you can see, we're switching for the unary address. It's a little bit redundant, but it has its pros to do this way. Unary address, return unary address, unary dereference, return unary dereference. These are not the same. This is the node type, and this is the opcode type, so don't confuse them. Okay, so now let's recompile. Okay, when you compile, go ahead and fire up the Python, and let's do &1, and we get an error, but at least it's a different error. Now it says unknown opcode. Before that, if you recall, it said the unary op number is not supported or something like that. Now it's a different one. So we successfully passed that stage. Now we are hitting something different. And it's been an hour and a half, and I think you deserve 5 to 10 minutes of break. And we're gonna proceed after that. Okay, are we all here? Okay, I think we can proceed, right? Okay. So we left off here on the unknown opcode. For those of you who are trying to catch up, all of you do the same thing. If you missed because you had to wait until the repo gets downloaded, what you can do, you can apply all the patches 1, 2, 3, 4, 5. Before that, make sure that everything is reset, so the repo is in brand new state. Apply all the patches, then do make regen-all. Okay, and after that compile, and you should be caught up by that. Okay. So we left off, on unknown opcode. Unknown opcode is actually very interesting. It originates in the file called cval.c. Cval.c is this file, cval.c, is the beating heart of the Python programming languages. This is the Python virtual machine itself. There's this function called pyeval underscore eval frame default, which is roughly 3,000 lines of code, 3,000 lines of C code, and this is the giant switch statement inside a loop. So if you open the cval.c at the line 890 and scroll down a little bit, you will see that sooner or later you hit, there will be a comment saying the main loop or something. Yeah, this is labeled main loop, and you loop forever until there is something to execute. You fetch an opcode and you do a switch on the opcode. There's a lot of other things happening which we're not interested in. There is a switch, and this is the fattest thing, the fattest part of the function. As you can see, it switches on every single opcode that exists, but since we added an opcode, it does exist. Our opcodes do exist. It spits out unknown opcode because we are not handling it inside a switch. If I search for this precise string, so let's do search unknown opcode. This is the line that triggers the error. As you can see, it switched all the cases, all the opcodes, and as you know, if nothing matches in the switch, it goes to a default. And this is what's happening here. It goes to default and just throws an error unknown opcode. So what we need to do now is the whole pipeline is working, but we are just missing the implementation of, we're not telling virtual machine what to do with the opcode, but the opcodes themselves exist. So what we want to do is we want to apply, I believe it's 6, right? Go ahead and apply patches 6.patch. What we did here is we added, we added two new cases. The first, this target, what do you see? Target is a macro. It has to do with something I'm going to explain in a moment, but it's basically it's a hidden. I'll explain that. So you have we have added the handling of the unary address and unary dereference, and what I want for now to do is whenever I hit that expression, I want it to raise an not implemented error. So go ahead and compile. Let's run Python. $1, and it still says unknown opcode. The reason for that is not really obvious if you don't know what's going on. The reason for that is Python virtual machine, as you can see, it's a switch basically. It supports 2 modes. The first mode is a switch statement, very basic. The second mode is, however, not available everywhere. It depends on your specific compiler. I believe everyone's using GCC on the Mac. If someone is using Mac, it's probably Clang, but I don't think it'll be working for you. On GCC, which we all use, I suppose, this is called GCC labels as values. Yeah. So this is another way of implementing switch, but a lot faster. So it is very handy when you implement sort of systems when the heart of the system is looping in a switch, like looping and switching. This is a lot faster way to do this, approximately 10 to 15% faster than the switch, because of how switch is implemented in compilers. It has to be safe, and because it has to be safe, it is a little bit slower than this one. In this version, you have to handle some things yourself, and if you don't handle them, you'll crash, but you'll be faster. So what we are missing that part. I'm not going to go deep into the details how this specific thing works, just for you to know that it exists. There are two modes. The first one is switch. The second one is called labels as values. Only if it is available on your compiler. On my compiler, it is, and it is used by default if it is available. You can force to omit it if you do configure. So configure help and grep for computed. Yeah, there is a switch it says with computed gotos. If you want only switch, you don't want the other way, you can do, but don't do this, just for you to know. You can do configure -- with computed gotos equals no. In that case, it would work. We're going to go the other way. We're going to add that thing that's missing, and we're going to proceed. So go ahead and apply the next, I believe, 7th patch. So just for you to see, we added opcode targets.h. We added 2 new lines. It has to do with how this feature is implemented. We're not going to go into the details, just for you to know that this thing exists. And go ahead and compile again. Okay, after you compile, run Python. And now you should see the not implemented error. So we are successfully parsing new expression. We are successfully optimizing it. We are successfully compiling it, and we are successfully executing it. If you recall, all of the execution is just throwing this exact error, because we have to connect it with the new built-in object, which we'll be implementing shortly. It doesn't exist yet, so therefore we just raise not implemented error. If we do ampersand, we should get the same, but for a unary address. Cool. I think that's worth an applaud. Okay. Before we proceed, I'm going to start the next chapter, so to speak. Before we proceed, any questions, any problems I can help you with? Okay. So now comes the second part of this tutorial. I'd say the most difficult one, but the most interesting one. I'm going to go back to the presentation. So we added new token. This was long ago. Now we are getting into the Python object system. Because if you recall, we are trying to implement a pointer object. It doesn't exist yet, but we want to make a new built-in object. If you recall, an expression evaluates to something. In Python, everything is an object. Therefore, an expression evaluates to an object, and we are missing the pointer object. We'll be implementing that. Before we start implementing that, I need to do a little tour on what is PyObject and what is PyType object and how the typing system works inside Python. So there is a struct called PyObject. You've heard that everything in Python is an object. This is where it originates from. It originates from lines 105 through 109 inside include/object.h file. This is the declaration of a PyObject struct. Every PyObject, this is again in C, every PyObject has two fields. The first field is reference count. How many of you know what reference count is? Okay, I'm gonna explain it later as well. Reference count and a PyType object. So a PyType object is a special object which defines the type of the object, but there's a catch. Before the catch, there is another type of object. It's called PyVar object. It takes PyObject as a base. Again, this is the inheritance built by hand, because you include PyObject inside every other object, therefore making every object an object. Right, so they share the same layout in the beginning. There's a PyVar object. This is for objects like lists, tuples, dicts, which internally have some sort of a variable part when you have multiple things they point to. And this is the type object. Now, if you recall this one, PyType object. This is the type object. This is the biggest object in Python. It has, if you can see, the first line is PyObject var head. This is a macro. This macro results into PyVar object. So basically, if you recall the PyVar object, it's going to get complicated, I know. If you recall the PyVar or object, it has a PyObject as a base, right? So therefore, a type object is also an object, right? Am I right? Yes. So it means that the object, every object has a pointer to a type, right? But the type itself is also an object. And this is where it gets even more complicated. This is the definition of a type. So if you recall, in Python you have a type function. It's not really a function, it's a class. But because it can be called, we'll treat it as a function, right? So this type is actually this struct, right? This. Now, what's funny is this struct starts with this macro PyVar object head in it. It's just some, just to reduce the amount of code you type. If you look at what it results to, you will understand that it creates an object and it fills in the reference count, which is 0, and the type of the object. But the type of the object, if you look closely, is itself. So if you have a type, it is an object, but the type of it is the type itself. And you can see this in the code. So if I type type of type, there will be a lot of typing. You'll get class type, and you can go as long as you want. You can exhaust all your memory. You'll get back every time back to itself. This is where the typing system sort of hits the dead end, because there has to be a dead end somewhere. This is how it's implemented in Python. So remember, every object has reference count and a type, and the type itself is also an object. So far, any questions? Is it getting harder? Okay. It's gonna get even more complicated. So as I said, this is the biggest object inside Python. The reason for that is because the object, the type object, defines all the behavior for the Python object. So what I mean by that, you know that you can overload operators, right? You can do class, blah, 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 double underscore add, double underscore sub. You have these magic underscore methods. All of this is inside a Python, as you use it in user space, you create yourself. But if you're implementing a built-in, it will be reflected in these fields, which are called slots. And you can see, for instance, there is a comment, methods suites for standard classes, PyNumber methods. This is the structure that holds like fields that pi number add. This is the function that will be responsible for adding a pi number, subtract, and so on and so forth. So all the behavior that Python object has is defined inside its type. So what we need to do, we need to add two objects. We need to add a pointer object, and we need to add a pointer type object, right? Because we want our object to have some behavior, right? We don't want to for it to just exist. It will be pointless. Okay, yeah. Now what we have to do is apply the next batch. I believe it's 8. Is it 8? Okay. So after applying 8 patch, what changed is we added two new files. First file is pointer object.h. It will be inside, as you can see, it's inside pointer object.c is inside objects, because this is the directory where all the built-in objects are defined. And this is the header file for it. This is an API, so internal API, so that what methods are going to be available for creating or manipulating with it. We will have a PyPointer new. It means that I want to call this method inside my switch, if you recall. Every time I hit that opcode, I want to create a new pointer, right? And every time I hit an opcode for the reference, I want to dereference a pointer. This will be functions that will be called there. Then I have pointer object.h inside include CPython. This is the should I say definition, declaration? I always confuse those two. Okay, declaration. This is the declaration of the PyPointer object. Recall, we have PyObject, and all other objects are called. This is a convention. This is a convention to call it PyXXX object. This will be a pointer object. It has a macro PyObject head, which is just some initialization. It just places a PyObject as a base. And there's another field, which is a pointee, the thing that we're going to point to. And it will be any other object. We'll see. Now pointer object.c. This is where we define this is where we implement our, if you recall, PyPointer new, PyPointer dereference. We implement a wrapper. How many of you know what a wrapper is inside Python _wrapper? Okay, this is the string representation of an object. So for those of you who don't know, if you create an object, print it, it will print blah, blah, blah at address. You can override it. You can do a represent, and you can return anything you like. This is how we do it inside C. Okay, let's go through this. This is PyPointer type. This is the type of our pointer, because if you recall, you have an object and then you have a type object separately. This is the bare minimum you have to have in order for an object to at least exist. We're not doing much, but at least it exists now. So we define a pointer type. The type of it will be type itself. Does it sound logically? So if you have a list type, what is the type of a type object? It's a type itself, right? So we do this the same here. Its name is pointer. The name is what you see in the inside the arrows. So if you see this class list, this list string is actually a string literal inside C. This is it. This is internal. It has to do with how many bytes you need to allocate for your object. This is the wrapper function. If you recall those slots, we are filling in those slots. So I'm filling in TP-repr, which stands for type representation. So we have a function that represents it. We have type dalloc. It is for the life cycle of the object, because sooner or later your object will be deallocated, will be removed from memory, and you have to define a function that handles it, because every object, when it's being deallocated, behaves differently. So in our case, if you recall the reference count field, do you recall it? Inside PyObject struct, what it means is how many objects inside Python are interested in me. If there is at least some, it means that the object needs to live, because if it's get removed, then you're gonna get into trouble, you're gonna crash. If there is no one interested in me, it means that the object can be safely removed from the memory. This is how the memory management is implemented in Python. We're gonna get more into the details of how it works later. And there is a TP flags. This is just some things that you just have to set. You don't really need to know why it has to be like that. So if we, did I go over? Yeah, pointer repr, pointer dealloc. So when we deallocate an object, we want to decrease by 1 a reference count on an object that we are pointing to, because logically we are not interested in it anymore. And this is the macro pyclear, which does that. It does it in a safe way, because there are some really edge cases when you can screw up, so you better call these safe macros already defined for you. And then you do the PyObject del, which is a function that's responsible for deallocating. Okay, PyPointer. These are the functions that we will be calling from inside the virtual machine, the switch statement. If you recall, what we want to do is we want to pass in here, we want to pass in an object that we are trying to create a pointer to. And what we want to do is we want to create a new pointer, set the pointee to the object that we want to point to, and return it, right? So we create a new pointer object. This is a standard check. If you run out of memory, you have to return null all the way up. This is how, by the way, the error system works in Python. You just return null all the way up to the virtual machine, and if somewhere something is null, it means that there must be an error, and this is how it reports an error to you. So here we set the pointee to the object we're trying to point to. We have to increment the reference. Now remember, if we are holding a reference to something, we have to increment its reference count, because if we are one short, it will be deallocated sometime in the future. And if we try to access it, it's still accessible, but it was deallocated, we're gonna crash. So it has to be 1-to-1, like mapping. So how many objects are interested in me? So is the reference count. And this is just some casting for a compiler to be happy. What else did change? I believe. Yeah, now that we have these new and deref, we no longer need plugs in our AST optimizer, because we now already know how to produce a value from a constant expression, right? So if you go to AST op, instead of the plug, we now have these two new methods, PyPointer new, PyPointer deref. And if we go to the cval, which is the virtual machine, the switch statement, we no longer have an error, not implemented error, but instead we implement these two methods, right? PyPointer new and PyPointer dereference. This top, Python is a stack-based machine. How many of you know what a stack-based machine means? Okay, so it is a sort of a model of computation. It goes back to Turing machines. How many of you heard of Turing machines? Okay, so the model of computation for Python is a stack-based machine, and basically you don't really need to go into the details. If you're implementing a unary operator, it will behave exactly the same as the other unary operator, right? It's just the implementation is different of the what it does, but how it interacts with the stack will be completely identical. So you get a value from the top, you do something with it, and then you push something back onto the stack. So this is popping from the stack. It doesn't pop. It does top. It's a little optimization for, because if you pop something and then you push something, you don't really need to do those things. You can just read from the top and then override what's on the top. This is a little implementation, like optimization. Okay, so this is popping, creating an object from the value. Now, if we have, for instance, %1, in this scenario, we're gonna hit unary address of 1. It means that the 1 as an object will be on the top of the stack. This will be the object will be popping off the stack. And we're gonna create a pointer object to that object. Then we're gonna decrease the reference count on the value and put it back into the stack. And again, if something bad happens, you return null. And this is the dispatch. This is for, if you recall, the computed gotos. This is the way how you handle it without the switch. If you do the switch, the dispatch macro results to nothing. If you do the computed gotos, it does what it's required to do for that implementation. So if we go ahead and try to compile, any questions so far? Okay. Okay, after you compile, let's try to do the $1, and you get an error. Cannot dereference non-pointer object, which makes sense, right? We can dereference only pointer object. Where does this error come from? If you go back to pointer object.c, here in PyPointer dereference, there is a check. This is a check that we added as well. It checks for the type of the object. If it's not a pointer, it will set an error and return null. So this is where this error comes from. If we take an address of, you can see we get a pointer to an integer. This asterisk int is what you get from this function, PyPointer wrapper. Briefly, what it does, it loops until it hits, it loops on a pointer until it hits something that is not pointer, and it just adds the asterisks, and then it grabs the type of the object and concatenates and returns as a string. Make sense? So I can in fact create as many pointers to an object as I want. So I can create 10, 20, as many as you want. And also I can dereference it. So if I let's say do a, which is a pointer to an integer, I can dereference a, right? And dereferencing just grabs the thing that we are pointing to and returning it. But you can go as many as you want. You can, again, try to dereference twice. You should get an error, right? Because if you dereference once, you get an object, the real object, and you cannot dereference non-pointer anymore. But if you do 1, 2, 3, 1, 2, 3, oops, you cannot. It's in the wrong order. So it kind of cancels out, right? Okay, cool. It's not really useful so far, but at least we have a new object. So we have a new piece of syntax that is parsed, it is compiled, it is executed, and it returns a new object. Now all we have to do is, what do you think we have to do? We lack some behavior on the object, right? So if I want to make it like in C, I want to be able to manipulate memory, right? So I'm pointing to an object, but I cannot manipulate its memory yet. So let's go ahead and add it. Actually, no. Actually, there's one thing that I forgot to do. This is all working perfectly, but there is one very terrible thing that happens underneath, and we're not realizing it yet. If I go ahead and create a test file. Let's do test.py. What I want to do is I want to loop infinitely. I want to create an array, and I want to append to the array the pointer to itself forever. Does it make sense? Now, if we go ahead and run it, python.exe test.py, it runs, everything's fine. If I go ahead and inside another terminal tab, which is also in the Docker, it has to be in the Docker. If I go ahead and, how many of you know what a top command is in Linux? Okay, it allows you to explore the processes, the CPU, the memory, etc. If I do the top, I can see that we have a Python process here. But what's really funny is, now it's first. Okay, we have a 100 CPU, which makes sense. We're running in a while loop. But the memory is growing and it never shrinks. So if you leave it for some time, it will consume up to what is the limit for the program, and the OS will kill it. Okay. If I, for instance, change it to be not pointer, but the array itself, right? And rerun. And again, let's explore. We see that we are 100 CPU, logical, but we are at constant memory. So it means that the memory gets recycled. Now remember, every object that no one is pointing to, no one is interested in, gets collected, memory gets collected, which happens every cycle in the loop, because we create X, we append X, and then after the loop ends, sort of X gets deleted and the memory gets reclaimed, and all over again. So we are looping, we are reclaiming memory. In the first scenario, we don't. Who knows why? Take away the ampersand. What do you mean? I don't know the answer to your question. Anyone? Any ideas? What's happening? Once again? The reference count's not dropping. Anyone else? Okay, actually you're right. The reference count is never dropping in the first scenario. To illustrate that, I built a package. It's pip installable. It works only for x86 and Python 3.9. Never tested on other configurations. Don't guarantee it to work. What it does, it allows you to, it patches Python in runtime, allows you to hook into the process of the allocation and provide a callback. So whenever an object is physically removed from the memory, your callback is triggered. So you can pip install it. It's Wolfram alf-idk. IDK stands for I don't know how to name it. So it is on GitHub. If someone is interested. So hook into process of Python object deallocation. I can, if you're interested, I can later explain how it works, some binary patching going on underneath. But what we want to do is we want to install it, and the way you use it, you can import it, import IDK. You provide a callback. Let's do a callback. It receives the ID of the object. And what I want to do is I want to print to the standard output that the object was deallocated. Right? Now, when I append array into itself, I want to register it. The way you do it is you do the watch method, IDK watch, and you watch for the X. You watch for this object, and you provide the callback. Okay. Now, if I run it, I should be seeing messages that the object is deallocated. And we can see that's the truth. Now, however, if I stop it and do the same with pointers, right? We had an issue with the pointer. And run it, I can see no messages, which proves that the object is never reclaimed. Any ideas why? Someone told the reference count is never dropping. Yeah, the reason for that is the reference count is never dropping. What I mean by that is when you have two types of objects in Python, you have what's called a container object. These are the objects that can reference other objects. These are lists, dicts, sets, etc., etc. But in our case, we have, if you recall the declaration, we have this pointee object, which is a single object we are referencing to. But again, it makes our object to be a container, right? Because we are referencing other objects. And what's happening underneath is the reference count of X is dropped, but it's being referenced from within itself. So you have an array and you have a pointer to the array, and then you have an X, which means that an X is pointing to an array and a pointer to that array points to the array, right? So you have two. Let's actually go ahead and, how many of you know that there is a getRefCount function inside sys module? Okay, from sys import getRefCount. If we create a list, I can do getRefCount on X, which is 2. The reason for this is 2 is because when it's passed to the function, the reference count is increased because you're passing it somewhere, right? So you will always see the real reference count will always be 1 more. There is, however, some exceptions to this. If you do reference count for instance 1, you'll get a big number. Any ideas why? There's other things using 1. That's correct. Because 1 as a constant is participating in many parts internally. This is why it already exists. It didn't create it. It took it from the cache, and it's basically we're using it. So this is never created again. And the reference count is high because many parts internally inside Python are referencing it. So just for you not to get confused why you get a nonsense. Okay. So back to our example. If I append a pointer to an object to the list, get ref count of x is 3. Now real one is -1, which is 2 logically. Now if I delete x, I deleted a variable. A variable is a string associated with a value. So the reference count went down to 1, but it will be never reclaimed because it is being referenced from within itself. We no longer can access it ourselves, right? I no longer can reference that array, but that array is still being referenced within itself. And because our pointer object, it will behave well, but for now it doesn't. And because it doesn't behave well, it keeps objects in memory like the cycle, okay? And therefore, Python can never reclaim the memory because it thinks that something is still interested in that object. So the way you fix it is actually pretty simple. I think it's the 9th patch. Yeah. So what we did is really minor changes. The first thing is we are not creating an object like the previous time. We're creating a GC, which stands for garbage collection. There are 2 ways of managing memory in Python. The first one is reference count. The second one is a tracing garbage collector. This is why it exists. It exists only to break cycles. There's no other explanation why this garbage collector works. It could be, the question is, can only the garbage collector suffice? It can. But the reason for 2 methods of managing memory is that removing reference count would introduce breaking changes. Therefore, they had to do this unpopular choice of basically supporting 2 ways of managing memory. Now after you create this GC new, which adds, I'm not going to go into the detail how it works, but it just creates an extra memory for the garbage collector to add it to a list of trackable items. You track the object, and when you deallocate the object, you want to untrack it and clear the reference and delete it you no longer delete it like regularly, but you have to do pyobject gc delete, okay? And there is 2 special methods that garbage collector will call. It expects you to have them. If you support garbage collector, before we didn't support it, now we do support. Our object does support. Not every object supports garbage collection because non-container objects do not need garbage collector because there is no way there will be a reference cycle, okay? These pointer traverse and pointer clear are internal like implementation of garbage collector. It calls into these methods to clear the break cycles. You don't really need to understand the specifics behind it. And additionally, what changed is we added a new flag, which is required once the object supports garbage collector. It has to have this flag. And we add these 2 methods. Again, these methods, as I told, the type object defines all the behavior. That's true, but it also defines all other internal things, and this is one of those. Okay. Now, if we compile, so what we did, basically, we added garbage collection support to our object, which didn't have it. If I go back to the test. Now this previously didn't work. There were no messages, if you recall. Now if I run it, oops, you can see messages start popping up. And to validate it even more, I can run it and Now let's explore the process. And as you can see, CPU 100 and the memory is constant, doesn't go anymore. Any questions so far? Okay. So this is not really fun so far because we're basically trying to make the object behave well. We're not yet getting the most fun part, which is coming. There is, however, one more issue, and this will be the last one. Then after this comes the most exciting part. It still has issue with the collection. If I do something like this, if I create a pointer to some object, and let's say I'm gonna for 99 times create the pointer to itself. So I'm basically creating a big linked list of pointers, right? And I want to print it. Okay, that's fine, makes sense, right? But if I increase the number, it's fine. Increase it even more. It's fine. One more. Fine. One more. And we get a segmentation flow. Any ideas why? So it does work, but after a certain, let's say, threshold, it doesn't. Any ideas why? What was that? Out of memory? No, it's not out of memory. The ref, no, it doesn't. It has nothing to do with ref count. What is it? Does it exceed the size in? What do you mean exceed the size? No, it doesn't. Yes. Yeah, you're right. So if you think about it, we have something like this, right? With the code. But if you recall how the memory management works, we have an variable x which points to the next pointer, which points to the next pointer, and so on and so forth until until you point to the list, which means that every single object has a ref count of 1, right? Because you get it, right? And the trick is if you go to pointer.c, the issue is in this pointer dealloc function. What it does, it untracks the object, then it clears reference, logical, right? Because we are no longer interested in what we are pointing to, so we need to decrease the reference count, and then we deallocate itself. But when you decrease reference count to 0, what's going to happen? This is the macropy dgraph, this line. So if you decrease reference count and it is 0, it will go ahead and call the deallocation function. And deallocation function looks up the TP dealloc slot, if you recall, in our type object, and we'll call it with our object, right? So what's happening is the X is being removed. It goes ahead, it goes ahead, clears the reference on the object it points to. It drops to 0. Then on the object it points to, goes ahead and tries to deallocate. Then that object tries to decrease to 0, it points to, and so on and so forth, you know? So you're building up the stack. So sooner or later, you just run into a stack overflow. Any questions? Is it clear? Okay. This issue, however, is very common inside the CPython. And we can fix it very easily. Git apply, I believe it's 10th. 10th? There are two new lines. It's called PyTrashCan begin and PyTrashCan end. Trashcan is a mechanism inside CPython which allows you to avoid these scenarios. So there is a comment which explains a trashcan mechanism. When deallocating a container object, it's possible to trigger an unbounded chain of deallocations, as each PyDecref in turn drops the ref count on the next object in that chain to 0. Okay, so the way it works, after a certain threshold, it stops recursing. It will put the object into a waiting queue, unwind the stack, and basically repeat the same process. So you're sort of limiting the stack size. That's it. If you compile it, and if you run it, you should no longer see this issue. And in fact, I can go as long as I want. I won't be getting this issue anymore. Okay. Any questions? Okay. Now comes the most interesting part. This will be the last patch we will apply. Now I have to mention that we've created an object that behaves well and safe from Python perspective. So it supports garbage collection, it supports the trash can, and it's basically it. You don't need anything else in order for it to be, in order not to get some unexpected crashes, and you don't know why. If you go ahead and apply the next patch, we are modifying the pointer object.c. What we have added is we have added this TP methods slot. TP methods means that I can call a method on an object, so an object.method. If we go ahead and explore this pointer methods, it is an array of one method, which is called bytes. And this is the handler for the method. What it does is it takes a object you are pointing to, takes its bytes, and returns you a byte object inside Python. So you can see the raw bytes of an object you're pointing to in the memory. We also have TP as mapping. TP as mapping is a suite of methods that is called whenever you do the subscription stuff. You know what a subscription means in terms of programming? So a subscription means this is the subscription. So you basically square brackets and some index. This is the subscription. So what it in our context, this subscription means give me a byte of an object you are pointing to at specific index. As you can see, there is pointer subscript. I take an item as in Python integer. I convert it into a C integer, and I index into the memory at that position and return it as a byte, as a number. What else is in this mapping? You also have MPS subscript, which stands for mapping assign subscript. So it is the same as this syntax. This will be triggered when you have this piece of syntax. The same you have in the double underscore, right? You have get item, set item. So this will be a set item sort of. So the assign subscript, what we will do, the thing you are trying to assign to, it will try to write into that position as a byte inside memory. There is a lot of checks going on. You can check it out later. But yeah, this is what it does. What else is get attribute? This is for when you do something dot something, or we don't need special handling for that. We can use already defined by object generic get attribute function. And I guess that's it, right? The bytes method, the reading bytes, and then writing bytes into the memory. Now remember, we're going to be writing into the RAM. So this is the point where our Python becomes unsafe. But this is also the point where it becomes really, really funny. So if we compile, let's run it. Let's create a pointer, let's say, to an array. Remember, there is a bytes method. I can do x.bytes. And now I can see the list object inside memory, raw bytes of it. Okay. This is the PyList object. It is in list_object.c file, list_object.h file. This is the definition of the list object, which has the PyObject var head. If you recall, PyObject var head is PyVar object, which has the op base and op size. So 2 fields. And then you have PyObject double pointer op items. This is how list object physically holds references to the elements inside of it. And what we want to do is we want to verify that these bytes actually make sense. If you recall the first 8 bytes, if you're running x64, 80x64, the first 8 bytes is reference count, right? So if we go back to the code, we can see that 1, 2, 3, 4, 5, 6, 7, 8 bytes. This is the 1. Do you know why the 1 is in the front instead of the end? Byte ordering, yeah. We are, for those of you who are on ARM, I don't think it's working anyway. So we all have the same environment, I guess. We all have x86, and x86 is a little endian, so the byte order is reversed. If I, for instance, create an array, take a pointer to it, again, let's explore bytes. We have 2. Actually, let me restart. Right, we have reference count of 2 because a variable is interested in the list, and we are also interested in the list, but through the pointer. If I create another variable, let's do z equals to let's do equals to a. Okay, so now we have a and z both pointing to the array, and if I explore it through a pointer, I'll get 3. So we can see that it really makes sense. If I delete z, so reference count should drop to 2, and we can see that it does. It drops to 2. Now I want to verify one more thing. As you can see, first 8 bytes is reference count. Do you recall what next 8 bytes mean? If you recall the PyObject, what 2 fields did PyObject always have? Type. No, the PyObject, not the type. So you have a reference count and a type. So it means that the first 8 bytes is reference count, and the next 8 bytes is an address of the type it's pointing to. So since we are exploring list, it makes sense that these 8 bytes are an address of by list type. So if I go to list object.c, there is a definition of PyList type. This is the PyList type object. This is the same as list. This is it. And I want to verify that this is it. I can do an ID of list, right? So if you know, the ID returns the physical location in the memory for any object. And I want to convert it into hex. So I can do 2 bytes. And I want 8 bytes from it. And I want a little byte order since we are on x86. So as you can see, these 8 bytes are exactly the same as these 8 bytes, which means it is a list, indeed. Cool, right? Now what I want to do is I want to swap to arrays without even touching them inside Python. So if we go back to the definition of PyList object, you have this double underscore ob item, which is a pointer to pointers to item, but the references to the objects that list holds. And if we count, it's 8 plus 8, so it is an offset of 16. So this is from 16th byte in memory to 24th byte in memory, since the pointer is 8 bytes long. It holds references to other objects. So what I want to do is I will go to test file. And I want to create 2 arrays. The first array will be, let's do numbers. 1, 2, 3. And the next array will be strings. Okay, now I want to swap them. Okay, now we're going to implement the swap, but we are going to implement it through the pointers. So I'm going to take the first pointer to the first array, second pointer to the second array. And if you recall, from 16th to 24th byte, we have to swap bytes. So physically the first list will be pointing to the second list's items and vice versa. So for I in range 16 to 24, right? 8 bytes. Sorry, it's actually 24 to 32 because this is by var object. Because list is by var, there is additional size. Yeah, this is 24 to 32. Right, by object varhead, it has object type and the variable part. So it is 24, 8, 8, 8. So if we go through 24 up to 32, I'm going to grab byte from the first array at the index. And for the second array at that index, I'm going to set it to the first byte at that index. And p1 I equals dmp. Oops. Okay, so we are physically swapping bytes in the objects. And if I run it, so we have before swap, we have 1, 2, 3 numbers, strings 1, 2, 3, and after swap, something's wrong. What's going? 24, 32, TMP. Did we compile? 24 plus 8. What is it? Temp. Okay. P2. Yeah, that's right. Okay. Now there you go. We had numbers as numbers, strings as strings, and after swap, objects are still the same, but we changed bytes and they're pointing to different objects. Okay. Cool, right? One more thing we can do is, as you know, strings in Python are immutable. So if I define a string as, let's say, hello, and I can take a pointer to that string, I can explore how it looks in the memory. So you can see there is a bunch of bytes. We're not interested. And here we have the actual string, literal hello. So if we take the length of it, we see that there is 54 bytes, which means that this is the 53rd position, 52, 51, 50, 49, 48. So if I do pointer at 48 position, it gives me 104. And if I convert it to a character, it should give me an H, right? But I can set it to, let's say, K. Okay, and I haven't touched the string, right? So if I print the string, it is all of a sudden Kalo instead of Halo. Okay. So these are the things you can do with pointers. It has no use at all. It will be never added to Python, but it's very useful when you learn CPython because it is a lot easier to explore bytes inside Python interpreter than recompiling stuff and checking stuff in the debugger manually. So this is really handy if you do the CPython development, and just for the heck of it, why not? And I guess that's it. You can go ahead and play with it yourself. You can find me there on GitHub, Discord, and LinkedIn. We have to sync on, for those of you who didn't follow. How many who didn't follow? Couldn't follow. Okay, a couple of you did. You can approach me. We can agree on. Actually, all of you. I'll be making a GitHub with the steps that we did, so we can reproduce it. So I'm not sure where we are all as a group. We don't have Discord, right? We don't. Okay, I'll figure something out. I'll ping you somewhere. I'll ask the organizers how to do this. Oh, thank you and have a great day.